everybody, and welcome to this OCA webinar about OCPP 2.0 Lite. My name is Hanna Kolotzek. I'm the Communications Officer at OCA, and I will be hosting this webinar today. Frank Buvel from OCA will present today, and in the end we will also have a Q&A session. So if you have any questions for us, please post them in the questions box on the right side of the webinar panel. So Frank, when you're ready, you can now start your presentation.
Okay, thank you very much, Hanna, for the introduction. So, today I'm going to tell you a bit about the OCPP 2.0 Lite paper that OCA has just published. At the request of some members, we started earlier last year a task group to examine OCPP 2.0 Lite. It was based on the concerns of some members that didn't think that OCPP 2.1 would fit on their microcontrollers. So we said, okay, we think it can still fit on a smaller footprint, but let's see how you can do it. And in the coming half hour or so, I will try to tell you more about this. So OCPP, of course, is a protocol that's meant to be used for any charging station, whether you're at a small home charger or an ultra-fast charger. So, and this means that there are a lot of features and requirements in OCPP that may not apply to smaller stations. So let's first discuss a bit what is OCPP 2.0 Lite. Well, it is a minimal implementation of 2.1 that is still compliant to the OCPP 2.1 core profile. And so you will be able to get a standard certification for it. And this minimal implementation is meant to fit on a resource-constrained device. That are devices that have a limited amount of RAM, ROM, and flash memory, and usually also a CPU that's not that fast. And it's the kind of systems that you see in residential charging stations, home chargers, for example. And also, for example, in cost-effective solutions that might be used for charging scooters and three-wheelers. And at the moment, we see that the industry is mostly using OCPP 1.6 for these systems. And that specification is already 10 years old. But it's a fairly compact specification, only around 150 pages. And OCPP 2.1 was published in 2020, is much larger. It's in fact, the documentation is about 10 times as large. And this might give the suggestion that an implementation will also be 10 times larger. But of course, as you may have guessed, I'm planning to show you in this webinar that does not have to be the case. So how big is OCPP 2.1 really? I mean, there are a lot of advanced features, but they are located in all kind of different profiles, we call them. The profiles are related to the certification program. And if you want to certify your implementation to be OCPP 2.1 certified, then you have to say, okay, which profiles am I certifying? And you need at least the core profile, that is for basic charging. And that contains things like security, provisioning, authorization, transactions, remote control, the familiar stuff that you need in a basic charging station. But there are a lot of advanced features like reservations or smart charging, 15.11.8, advanced security, etc., that are not necessarily part of a core profile to have to be part of your implementation. And then even within the core profile, there are still many optional features that depend on your hardware configuration, for example. For example, if you have a fixed cable, some things might not be needed to be implemented. Your authorization might only support RFID readers and no other methods, or maybe you only have a start-stop button and no RFID reader. You may not have displays, etc. So there are many things that the simpler your station is, the smaller even your core implementation is going to be. And as a result of that, you will see that a minimal OCPP 2.1 implementation can be of comparable size to an OCPP 1.6 implementation. Now, of course, I usually get the question, why should we upgrade to 2.01 if 1.6 does the job? Because of course, OCPP 1.6 is capable to control your charge. I mean, that's been shown all around the world. But as I mentioned, it is a 10-year-old specification, and the e-mobility business is quite a fast-moving industry, and a lot of things are changing. All new developments are now taking place in the OCPP 2.x line, 2.01, 2.1, and further releases probably to come in the near future. So we see already at the OCPP 2.01 we added support for the device model, which offers much improved configuration and monitoring of your station, and a more extensive transaction handling mechanism. And in 2.1, we now added, for example, 15.8-20 support, bidirectional charging, battery swapping, local cost calculation, and things like that. So a lot of enhancements being made in the 2.x line. And it's actually a really small step to go from a 2.01 to a 2.1 core implementation, for example. We've shown that recently in our webinar on OCPP 2.1. So if you're able to move to the Lite implementation, for example, then you're always ready to extend your system with newer features that are available in the 2.x line. And we see that industry is now, it's still going slowly, but it's surely moving towards the OCPP 2.x line. So that's why it's, even for smaller systems, it might be beneficial to move to this 2.0 Lite or 2.01, because you're simply more future-proof, and you will be able to connect also to future central management systems. So now about the resource-constrained devices. If we talk about resource-constrained devices, what kind of systems are we thinking of? I mean, it's basically microcontroller systems like the Espressif 32 or the STM 32 system. They typically have a few megabytes of ROM for firmware, 2 or 3 megabytes of ROM or something like that, and only a few hundred kilobytes of RAM for your stack and heap. And they also have a limited flash memory for persistent storage and a limited CPU speed. Well, it turns out that the CPU speed is not really an issue for OCPP, because OCPP is not really CPU intensive. You mainly use CPU to messages and start and stop some actions in the station, but that's all. That's it. So it's actually the RAM and the ROM size that is the limiting factor, and that's what you need to be minimizing. So what can you do there? Okay, if you want to minimize your ROM footprint, well, you need, of course, to have smaller firmware. To minimize your RAM, you need to reduce your runtime memory requirements. And to minimize your flash, probably your best way is to optimize your device model to minimize data storage. Okay, so I will go over these 3 items in a little bit more detail. First, how can we minimize the ROM usage? Well, one of the big things that you can do to reduce your firmware size is to avoid the need of an embedded database. Because if you're, for example, adding an embedded SQL database, that immediately increases your firmware size. And as we shall see, there are ways to reduce it, and you in the minimal implementation you can do without a database. I'll come back on that in the one of the later slides on the device model. Furthermore, you want to minimize your firmware complexity in general. The fewer functionality you implement, the smaller your firmware will be. So we will only implement the bare minimum core profile in this situation. And that means that you can limit the functionality of certain functional blocks, as we call them, OCPP, to an absolute minimum. In the white paper that we wrote about this, we go through all the functional blocks of the OCPP profile, so authorization, transactions, meter values, etc. I only mentioned these here, but we go through all of them and we explain which messages you could leave out to still be compliant to a core profile. And if you take, for example, the authorization functional block, then authorization supports many different kinds of authorizing, but in a simple station, you might only support a single authorization method. So only, for example, an RFID reader or only a start-stop button. And you probably also do not want to support an authorization cache because you don't want to spend your RAM on the cache memory for it. And if you do not have the cache, that also makes your implementation simpler because you do not have to be maintaining a cache and checking a cache for authorization. So these are some steps you can do to limit the functionality and the complexity and therefore the firmware size of your authorization part. The similar goes for the transaction functional block. The transaction mechanism in 201 is much more extensive. And one of the things that adds a lot of complexity has been the flexible start and stop point. So for those of you who are not familiar with it, in OCPP 201, you can define what condition starts a transaction. So you could say, okay, my transaction starts as soon as somebody authorizes at the station, or my transaction starts as soon as somebody plugs in a cable, or if a cable is plugged in and authorized. If both conditions happen, this is what we call the power path closed situation. If both conditions happen, that starts a transaction. This is actually, if you're used to implementing OCPP 1.6, the power path closed condition, where you're both authorized and plugged in, is when a transaction starts. Well, in OCPP 201, you can make that flexible also for other conditions. But if you want to keep it simple, then just say my implementation only supports a start point, power path closed, and a stop point, power path closed. Then you do not have to implement the logic to support all these different conditions. Because as you will have understood by now, it's not only the start point that's flexible, also the stop point can be flexible. But for our minimal implementation, we keep it simple. We say, okay, it's always power path closed, which is similar to the 1.6 model. And then we have the meter values, for example. There are a lot of meter values that you can support. And having a lot of meter values makes your messages larger during the transaction events when you're sending these meter values, and your configuration more complex. So you could say for a minimal implementation, I only support, for example, the basic energy measurement, the energy active import register. So these are a number of methods that will drastically reduce your firmware size. And at the end of my session here, in the Q&A section, we have one developers who have created a minimal implementation, and he might be able to tell you some more about it if you have some questions about this. Now, we also want to minimize the RAM usage, the writable memory, because that's even more limited on these microcontrollers. And here again, there are several things you can do to limit the amount of runtime memory. One thing we can do, for example, is to limit the maximum message size, because there are possibilities in the device model, in the configuration settings, where you can configure the maximum number of items per message that you support, or the maximum number of bytes per message that you support. So if you set this value, then this configuration value is going to be reported to the central management system when it requests a base report. So then the CMS knows, okay, I have to limit my message size, for example, to so many bytes per message. So this will also mean that as a charger, you can do it with smaller buffers for TLS, for example, or to unpack your messages. Now, our members that did some minimal implementation have also shown that you can save a lot of memory by avoiding data duplication while you're processing the message. So you can keep the JSON message in your TLS input buffer and parse it in place there, rather than copying it from the input buffer to your own memory and process it from there. So that also saves a lot of copying and memory that way. And one big memory eater is also the default 16 kilobytes TLS communication buffer. Because for TLS you need an input buffer and an output buffer, and they're both 16 kilobytes by default. So if you can make them smaller, you can save quite a lot of memory. You can easily save like 10 or 12 kilobytes of memory. And it's in many implementations not possible to negotiate the size of the TLS buffer with the server. But what you can do, you can unilaterally from your own side decide to reduce your output buffer. You can say, okay, my output buffer, which is default 16 kilobytes, I make that only 2 kilobytes. And we have done some tests on OCPP messages based on many certification runs that we have seen until now. And it shows that about 99% or 99.5% of all messages or so fits in a 2 kilobyte output buffer. So it's fairly safe to do that. And then there is the persistent memory, the flash memory that you also want to minimize or avoid that you wear it out. Well, as I mentioned, if you're going to use an embedded database, it takes up a lot of ROM memory, but it also takes up quite a lot of persistent memory. And what you want to do is you want to optimize your device model. And your device model is mostly about configuration settings, but also about reporting the structure of your charger. For example, it tells you how many EVSEs does your station have. And as a manufacturer, you can decide how much detail you want to put in your device model, how much you want to report about the configuration of your system and the hardware configuration of your system. but there are only around 50 components and variables that are really required by the specification. Many of these required variables that you have to report, they can be read-only because they are, for example, fixed. I mean, the amount of EVSEs and connectors that you have is fixed. You can report that from your firmware. It does not have to be stored anywhere. A similar situation is, for example, the availability state variable on a connector. I mean, the availability state, occupied or available, for example, that's of course a variable, but your firmware decides whether it's available or not. So again, that's something that does not have to be stored in the database. So it turns out that of these around 50 required variables, only 19 need to be writable by the central station, meaning the central management system, which means that the back office needs to be able to configure them. But this set of 19 variables, that's easily something that you can store in an ASCII text file, for example. So it can be very compressed, small storage here. Another thing that might take a lot of memory is, for example, the storage of offline transactions. If your connectivity is lost for a while and a transaction is going on, you want to start to save any transaction messages during that time. But it turns out, as one of our sample implementations showed, that you can reduce the storage for that at least a factor 10x if you simply use some compression. The data that you store offline, you can compress it, and then, for example, instead of using 600-700 bytes of storage for it, you only use like 50 or 60 bytes for it. That really makes a huge difference. So with this, I think we've shown that there are ways to reduce your ROM usage and your memory usage and your persistent memory. And if you do that, you're able to create a really compact implementation. And for this, two of our members have, as part of the task group that we are doing within OCA, two of our members have created a compact implementation, the micro OCPP and open OCPP. And I will shortly quickly introduce them. Micro OCPP was created by Matthias Axtaler. It's a fairly well-known open source implementation of the OCPP 1.6 protocol stack, and he has been extending it with the 201 support as well. And at the moment, this 201 implementation is about 2/3 finished, and at the moment it's around 150 kilobytes in size. He estimates that the full implementation, so when he's ready with the minimal implementation, it is going to stay well below 200 kilobytes. And it's then a stack that supports both 1.6 and 201. Now, he has done some measurements on that about the size. And when he's done with it, when the implementation is ready, we will be adding the full details of these measurements to our OCPP 2.Lite paper. We decided not to implement that, to add any unfinished details to the paper, because I think that's not might give maybe a wrong impression. So the paper that's currently published on our site, on our openchargealliance.org site, does not contain the details of micro OCPP yet, but you can expect an update somewhere in the coming months that has all those details. Another implementation was created by Cedric Shuey of Charge Lab in Canada. This is an implementation that's about to be open sourced soon. They're in the process of arranging that. And it's actually a complete charger binary for ESP32 that supports OCPP 1.6 and 201. The total size of this implementation is about 1.6 megabytes. And he told me that the actual application object, or the actual firmware for the OCPP functionality, is around nearly 500 kilobytes, and the rest of it is all the libraries for the microcontroller support. Again, once this implementation is going to be formally open sourced, then the full details of these will be added also to the OCPP Lite white paper. So as I mentioned, the white paper is already available on our website. If you go to openchargealliance.org and then to the menu white papers on the top, you can there look up the OCPP for resource constrained devices paper. And there it explains that it's possible to create a real world implementation of OCPP 201 that will work within like 200 kilobytes of ROM and 50 kilobytes of RAM. And that really makes it useful for low resource environments. So it will be updated soon with some measured data from both of these implementations. Another thing that I can announce that we are planning to organize an OCPP 2.0 Lite hackathon in India this summer, probably somewhere around July. The organization is still in progress, but the idea is there that we will provide a microcontroller platform and the open source implementation of both micro OCPP and open OCPP. And then the trick is who can make the best implementation on his low resource device within, for example, 2 days of time or so. So keep following us on the news announcement on the site, and you will see if when it's going to be organized, and maybe we can see you there. So now I get to the time where we can, I think, answer some questions. We have Matthias Axtaller present on the panel to answer any technical questions that you might have. So I think with this, I will hand over the control to Hannah again.
Yes, so thank you, Frank. Thank you for your presentation. So we will now start the Q&A session. And we also have a panel guest today, Matthias, who developed micro OCPP. So thank you very much for joining us. Maybe you can give a short introduction about your work, and then we can start the Q&A.
Hi, I'm contributing to the OCPP 2.0 Lite Working Group, and I've started micro OCPP as an OCPP library for microcontrollers, and started it 6 years ago, where OCPP 1.6 was around, and back then I decided to start with 1.6 because 201 it was the most widely used OCPP implementation. But yeah, time has really started to move on to 201, and I've seen some hurdles from the specification, which the Lite Working Group is to overcome.
Yeah, all right. Thank you for your introduction. So maybe we can have a look at the first question. Maybe this is one is for you, Matthias. How did you measure micro OCPP?
I measured micro OCPP under, let's call it lab conditions. There is a simulator for which runs on Linux, which allows for easier development, the OCPP simulator. And that's a C++ application which is similar to embedded firmwares, and so it's comparable to actual firmwares. The also to measure the firmware footprint, since C or C++ compilers, they use each source file and compile them into different independent compilation objects. And from those you can take the size, and then you can basically sum up which of those files belong to micro OCPP, which of those files belong to the environment. And then you can see, okay, what's the contribution of the OCPP stack to the final firmware binary. And for the RAM measurements, C also allows to monitor all malloc and heap free calls. So you can clearly see how much the OCPP stack and frees. And those two, I've done both for the white paper.
All right. Yeah, thank you. The next question is, how large would micro OCPP be in an implementation?
I also double checked the measurements with the microcontroller build artifacts, and it's roughly the same. On Linux, it's slightly more because you have 64-bit wide pointers, and you have a different STL implementation. But it's really mostly the same. There's no huge difference.
Mm-hmm. All right. Let's have a look at another question. So what exactly is part of micro OCPP? Is it only about messaging, or?
The micro OCPP stack, it includes the business logic of OCPP. So there is it implements the transaction state machine. It takes care of keeping the configurations and variables of OCPP, and to communicate to the server what the status of the charger is. And it also does everything from that point on to the server. So it also has the RPC mechanism built in, and it also serializes and deserializes. There are clear cutting points to the environment. For example, the WebSocket implementation is not part of micro OCPP, but that needs to be integrated per platform. For example, on very low resource platforms, you could have a TLS implementation inside your 4G modem, and then you could tell a micro OCPP to just direct all data to the existing WebSocket or TLS library, and save some memory for that. To exactly see where the cutting points are, you need to check out the GitHub page. There are a few options.
Mm-hmm. All right. Yeah, thank you. So let's have a look at another question. Is OCPP Lite only usable for small devices, or do you also see business cases for different chargers? I'm not sure who can answer this one. Yeah.
Is it a question to Frank or me? I can.
I'm not
I
sure
can.
which yeah.
Okay, so maybe Frank has something to add.
No, I think you were best to answer this, but yeah, in general, let me say that the 2. Lite is yeah, aiming at small devices, because if you have a much larger footprint in your controller, then you do not have to limit yourself to the light constraints. You can just implement more options in your OCPP implementation. So go ahead, Matthias, for micro OCPP.
Yeah, it's also about the development complexities, which are clearly reduced by OCPP 2. Lite. So if you're building mainly home chargers, but you chose a platform which has plenty of available ROM and RAM, then you could clearly see benefits of reducing the development time of implementing OCPP 2. Lite.
Yeah, all right. Thank you. Next question is it both 1.6 and 201, or can I get it only with 201?
I assume that is our micro OCPP. At the moment, there are only 2 operational modes, which is 1.6 only and 1.6 plus 201. Because there's still some overlap in functionality. Some 201 features, they reuse 1.6 code, and that separation hasn't been made to run it in isolated 201 mode. But that's work in progress, and that's as soon as the usage of micro OCPP changes towards a more 201 networks, then that will be introduced.
So Matthias, maybe I can also add a follow-up question on this then. So basically say your the 201 reuses a lot of the 1.6 functionality that's already in there. So yeah, basically the 201 adds a little bit on top of the 1.6 stack. Is that correct?
In some use cases, for example, the boot notification message and the functionality around boot notification, it is similar in 201. It only adds a few fields in the JSON message, and that's why I've reused it mostly in the 201, and then introduce if-else statement. If 1.6, then do this. If 201, then add a few fields. But generally, I think that it's easier to re-implement the OCPP stack when switching over to 201. The parts which really can be reused is the RPC messaging mechanism, and the business logic is a little hard to adapt for 201. Especially, except maybe it's the 1.6 implementation is so deeply integrated with other systems that it comes at an extra cost. But in case of micro OCPP, it's easier to start a new development of the business logic.
Yes, all right, thank you. Then we got a question about certification process. So how does the OCPP 2. Lite certification process run?
I think I will take that question. This certification for 2. Lite is actually a regular certification. When we started with the 2.Lite task group, we had the ideas like, okay, maybe we shall make a special light certification that allows for even less functionality to implement to become certified, and then you don't get a regular core certificate, but you get a light certificate. But it turned out that the few limitations that you could impose, we had a number of messages that, okay, you can omit this, you can omit that, that it was really marginal effect. It was not really worth the trouble, because then you can say, okay, now I have a light implementation and I save maybe 5 or 10% in firmware size, but you're not a full compliant OCPP, so you might not be able to to match with all systems. So it turns out that we think that most implementers, and this was also the case for Matthias and Cedric that created their minimal implementation, they decided, well, I could maybe omit these messages, but it only saves me a little bit. I rather have the full core profile, because then I'm much more flexible and have more possibilities to have my product used everywhere. So that's why we decided, okay, let's make it a full core profile. So 2.Lite is actually simply 201 core implementation with the bare minimum, but enough to become to get the normal OCPP 201 certification.
Yeah, all right. Thank you, Frank. Then we will get back to micro OCPP. We have a question, who's using it at the moment? So who's using micro OCPP?
Yeah, there are a few companies which I've worked with, and those are many of those are listed on micro-ocpp.com. Usually, I'm working under NDA, so that list isn't complete. But I would say it's half of the companies I've personally worked with. Since micro OCPP is MIT licensed, and I don't really care of companies reaching out to me and telling me, hey, we are using your stuff. I don't have a full statistics of the global users, but I know from the GitHub activity that there are many inquiries from India. So I assume that there are a few companies using it, and from time to time, so it's really hard to estimate. But I'm aware of at least 10-ish companies, and so that's how much I can answer.
So I'm Cedric Shui, I'm the Chief Architect at ChargeLab, and OpenOCPP is our open source firmware that is attempting to solve a real problem that we've seen in the industry, which is the fragmentation that we see across different implementations and the difficulty that different resource-constrained manufacturers have in coming up with a minimum viable implementation, either for 1.6 or 2.0.1, that is of sufficiently high quality. So what we've found, both in our original 1.6 implementation and our 2.0.1 implementation, is that there is a lot of, let's call it boilerplate, that a manufacturer must address to adopt a 1.6 or a 2.0.1 implementation that is table stakes across the industry. That doesn't necessarily provide them with a great deal of business value. And for that reason, we saw an opportunity to produce an open source implementation that could be adopted by different manufacturers to address some of those commonalities within their charger firmware. And our open source, or our previously closed source 1.6 implementation, is currently running on thousands of devices in the field. It's used by multiple manufacturers, and we're currently extending that to 2.0.1. So that was the initiative that that we took up along with the 2.0 Lite Working Group to move that into the 2.0.1 implementation and advance that project further. So let me hand that back to Hannah. Hopefully that was sufficient
Yeah.
introduction there.
All right, thanks for your introduction. So let's have a look at the first question. Maybe this one is for you, Cedric. What are the main functions of embedded software like STM32, for example, on the purpose architecture? Yes.
Sorry, can you repeat that, Hannah? I missed
Yeah,
the last
sure.
part.
So what are the main functions of embedded software like STM32, for example, on the proposed architecture? Oh, I guess maybe it's clearer like that. So proposed architecture.
Okay, so I might not have enough context there. I'm not entirely sure what the question is referring to, but the model that we typically see in chargers is the ESP32 module, or the likely STM32 module. Typically acts as the OCPP microcontroller. It runs all of the business logic for the charger. And typically the model that we see in different embedded applications is functionality is split across a microcontroller that acts as the OCPP controller and a much smaller targeted microcontroller, typically an STM microcontroller or similar, that physically interacts with the charger and controls the electrical elements on the device. And that is the model that and the architecture that we've commonly seen throughout the industry. So typically, the module that we're referring to here is the ESP32 module. It's the OCPP microcontroller. And the working assumption there, both I believe in the micro OCPP implementation and the open OCPP implementation, is that the control of the hardware itself is delegated to the manufacturer. And typically what that looks like for most manufacturers is there's a UART channel that's defined to a secondary chip that acts as their electrical controller and that the manufacturer can then use to ensure electrical safety. So hopefully that answers the question, but if not, then please clarify.
Yes, so maybe if we get another question about it, of course, we will ask it again, but I think it was clear. So the next one is maybe for Frank. How does certification work for OCPP 2.0 Lite?
Yes, I can take that. Well, actually, 2.0 Lite is a standard core, OCPP core certification. I will elaborate a little bit more on this topic, because when we started to investigate a light OCPP 2.1 implementation, we started out with the idea that maybe we need to use a separate certification for this, and even smaller than the core profile. So we allow certain messages to be omitted for light to make it even smaller. But it soon turned out that, for example, we did not want to leave out security, for example. I mean, even if it's a home charger, you need security, so that had to be part of it. And there were a few other messages that we say, okay, maybe we can leave that out. But it turned out that you maybe save 5 or 10% of it, of space, but then you have the problem that you're not really core certified, and that does mean that your usability is slightly less. You might not be able to use your implementation in as many situations. And it turned out that both for micro OCPP and open OCPP, they decided to make it fully core compliant anyhow, because they can probably do more business with it that way. And so then we decided, no, this is probably something that most implementers will go to do. If it only saves 5 or 10% and it still fits on your microcontroller, then let's make it full core profile. So we call it OCPP 2.0 Lite, which basically means it's a minimal core implementation, but it's a full official core certified implementation.
Yes, thank you for clarifying. Yeah, thanks. We got another question about Lite. Is OCPP Lite only usable for small devices, or do you also see business cases for different chargers?
Let me start, and then Cedric. I think
Go for it.
OCPP Lite can be used for smaller and larger charges, but of course, if you have a large footprint, then you can probably implement much more. So it's no longer really a light implementation. But let me pass it on to the real developer here in the room. Cedric, what can you tell about it?
Yeah, so we definitely see the possibility of using these types of light implementations in a variety of different devices. I think that in the industry as we see it at the moment, there's going to be, or we anticipate less appetite for an implementation like this in the DC fast charger space, where there already exists an open source implementation, Everest, that does address many of the full needs of a DC fast charger. However, for AC chargers, for home chargers, for commercial AC chargers, we do see quite a bit of application for these types of light implementations. Now, very often, the applications that a manufacturer may want to target there are going to go beyond the light implementation, just like they would in 1.6, because there's going to likely be a need for displaying costs on the display for at least monetized chargers in certain jurisdictions, and that will drive manufacturers or projects like micro OCPP or open OCPP to extend support for those types of messages and add in different elements that are necessary for that. But fundamentally, no, there is no limitation on the types of devices that can be targeted here.
Yes, all right. Okay, so let's have a look at the next question. Is there any specific implementation, so library or code, for OCPP 201 for microcontroller that you're trying to make compatible in the first place? So maybe that's also a question for Cedric.
Was there a specific 1.6 implementation that we were trying to make compatible with the 2.0.1 implementation? I think that's the question there. So I would say that there wasn't a specific charger that we were trying to make compatible with 2.0.1 when we move forward with our 2.0.1 implementation. That was more to address the potential market need there for an open source implementation, as well as to improve our own internal testing capabilities. Because exactly the same firmware that we developed for 1.6 that we developed for 2.0.1 can be used as a simulator, can be run in a Linux environment or a headless mode, so that we can test our own platform without the use of a real device. And that was the motivation for ChargeLab specifically to move forward with a 2.0.1 implementation. Now, we will be very likely deploying that to different real devices in the field at some point, and our partners that do use our firmware will likely adopt that at some point as well.
All right, thank you. So as far as I can see, we have now answered all questions that we got from our audience. So thank you everybody for listening and for asking your questions. And to Cedric and Frank, thank you for sharing your insights. If you have any more questions for us, you can contact the Open Charge Alliance. You can email us on info@openchargealliance.org, and then we can answer your questions and come back to you. So for now, I will close this session. Thank you very much for participating, and have a good day.
Thank you all. Bye for now.
Bye-bye.